So in the previous chapter, we introduced the work energy theorem, kinetic energy and work. And that allows us to find the effect of a force over space. And often it gives us a way to go from initial state to final state without knowing too much detail about the process. And that certainly was an advantage, as you've seen in a number of examples. However, the work energy theorem in itself does not quite relate you directly from initial to final state. If you look at the work energy theorem, the right-hand side, delta K, indeed is very clean. It only has two terms, the final kinetic energy and then the minus the initial kinetic energy. There's really nothing in between. But if you look at the left-hand side of the equation, it's not that simple. It's an integral of all the forces acting on the object going from initial to final, integrating over displacement dr. Now, in principle, this integral can depend on not only the initial and final state, but how you get there. It depends on the actual process. So unless you have a special way to find this integral, which we know in some cases are quite simple, such as the case of gravity, such as the case of normal force, in general, without knowing how to do this integral of force over space, you cannot quite utilize the work energy theorem. And like I said, this integral, in the most general sense, is dependent on the path. Now the question is, can we further clean up the left-hand side of the equation so that we don't ever have to worry about the actual process of going from initial to final? And we can establish, therefore, a direct link between initial and final. So you have the initial state, okay, an initial state, which we call I, and you have a final state, which we call F. You go directly from initial to final state with nothing in between. You don't have to ever worry about the process. Just give me the initial state, I can go directly to the final state. Or better yet, is there a quantity which does not change its magnitude, change its value from initial to final state? Okay, something initial, whatever that quantity is, initial state, and something final, the final state, and they're just equal to each other. Is there such a quantity? Okay, if this quantity exists, then we say this quantity is conserved in this process going from initial to final. This would be a so-called conservation law. You will see the first conservation law in this chapter, one of the three conservation laws you will learn in Physics 8a. Conservation laws are the crown jewels of physics. The importance of the conservation laws are really second to none when it comes to studying physics. You really have to keep this in mind. You will see countless examples of how conservation laws can really greatly simplify the process of solving problems. Okay, so we are really onto something really good. So let's get started about this process. How does one simplify this integral of the work done by a force? Is it possible that under certain circumstances, this integral is not dependent on the path from initial to final? It depends only on the initial state and the final state, but not on the actual process of getting from initial to final. Well, to answer this question, let's first take a look at some examples of actual forces. You know, there seems to be two types of forces when it comes to the work they do and the effect of the work they do. Friction is an example of one type. Gravity is an example of another type. Look at friction, for example. Now you drive your car, it's got kinetic energy, and then you hit the brake, the car slows down, it eventually stops, right? Now from the work energy theory point of view, we can understand what's going on. What happens really is just, friction does negative work on the car. Okay, so friction is backward. It does negative work on the car, and that slows down the car, eventually eliminating all the kinetic energy. Now, the work that you do against friction, or actually I should say friction does negative work here, which kills the kinetic energy. Do you get anything out of it? the kinetic energy that is lost due to the negative work done by friction. Do you ever get it back? And that is when your car is stopped, okay? Assume it's driving on a level road and friction eventually stops it. The kinetic energy that's lost in the process, do you ever get it back? Is it possible for your car to suddenly pick up a speed on its own without you stepping on the gas? No, we know that's not possible, right? It's just not possible. Whatever energy that's expended due to the negative work done by friction is simply gone. You never get it back. And that is one type of force, friction being an example. But there is another type of force, gravity being an example. Suppose now, consider this person climbing up, right? As he climbs up, he certainly is overcoming gravity, or gravity is doing negative work in the process, right? Negative work in the process, like in the first case, friction is doing negative work. But as he overcomes gravity by pulling himself upwards, the work that he does to overcome gravity, or we say the negative work done by gravity, is not totally wasted, like the case of friction. I mean, in the case of friction, the kinetic energy eventually turns into heat and sound. But in this case, is the energy that he expended to overcome the gravitational pull. Is that totally wasted? Well, not quite. As a matter of fact, as he climbs to the top of the mountain, this is where he ends up, okay? This is where he ends up, right? Wow, you're on top of the world, climbing up. But is that all good, necessarily? Well, to some of us, it's good. To others, it may not be good. Look at this picture. Okay, I drew some wiggly yellow lines to indicate that this guy is really spooked. This is called the fear of heights. Why are we afraid of heights? At least some of us are afraid of heights. Okay, where does the fear come from? We're not moving. We don't have any kinetic energy or anything, right? So why are we afraid of heights? Well, it's really because in the back of our mind, you know, the moment we lose our step, we'll be on our way down. Gravity will start to do positive work, right? And that's not a good thing. If we go back to this picture here, if gravity does positive work on its way down, like this, by the time you reach the same level, gravity would have pulled you, would have accelerated you, you would gain a lot of kinetic energy, and that's not a good thing. But you know, from the work and energy point of view, the work you do against gravity will take you to a higher elevation. And that means the work done that you did against gravity is not really wasted. Okay? It's not wasted, because that way you will be at a higher elevation, so gravity is now able to pull you down if you go back to the same level. Okay, so you get kinetic energy back. This is very different from the case of friction, and the work you do against friction is just gone. You don't have it anymore. Okay, so that's very different. So you see, in this case of gravity, this person standing on the top of the hill does not have any kinetic energy. But in the back of his mind, he knows that he can acquire kinetic energy back, or he has the potential to acquire kinetic energy. All he has to do is jump out of the cliff. And that idea in the back of his mind is what caused a lot of people to have fear of heights. Okay, it's the potential to gain kinetic energy. And this word potential, you will see that coming quite often from this chapter and on. So again, these are two distinct types of forces, but how do we distinguish them formally and mathematically? Well, turns out we can do so by examining what's called the work done in a loop. You consider the case of friction, for example. Okay, let me draw a loop of any shape. So let me do that. It's a loop of any shape. It comes back to itself. Okay, this contour, we call it C. The shape is denoted with letter C. It can be any shape. Now, in the case of gravity, I'm sorry, in the case of friction, okay, we start from somewhere in the loop and come back to the same point. How much work is done by friction? Let's say I'm using a stylus, right? My stylus is moving down along this path on screen. Every step of the way, my hand has to do work to overcome friction, or friction is doing negative work to resist the motion of the tip of the stylus. And as I get back to the same spot, because at every point, the friction does negative work. So overall, the work done by friction is negative, okay? Sometimes it's positive, friction does not always do negative work. But the point is that if you draw an arbitrary loop that's self-enclosed, the work done by friction usually is not zero, okay? Like in this case, it's negative, sometimes it can be positive. But anyhow, it's not zero, okay? So the work done by friction for this entire loop is not zero. That's something very important. I'm gonna write that down. F dot dr, generally speaking, is not equal to zero. And this is not just any loop. This contour is self-enclosed. So I use a little circle in the integral sign indicating this is a self-enclosed loop. Okay, it's not zero, right? But gravity is a different story. Gravity, if you start from any point here, let's say here on the loop, you take any contour, let's say this particular one. You go this way and you go that way. How much work is done by gravity? The total work done by gravity is mgh. H is a change in height, right? And the change in height is zero, of course, when you get back to yourself, right? I mean, if you look at, you go back to this diagram here, this picture here, if you start from, if you start from here, let's say this is your initial point. This is your initial point, right? You go up and you go down, and then you can, of course, you can complete this loop. As you go up from here to there, gravity is doing negative work. But then as you go back down to, to the same spot, gravity does positive work. So overall, the work done by gravity is zero. And this doesn't have anything to do with the shape of the contour. As long as you go back to yourself, okay, the work done by gravity is zero. So I'm going to write down this formula here. The work done by gravity about any contour is zero, okay? This is not valid for things like friction, but it is valid for things like gravity. This type of force, gravity being one example, is called a conservative force. I'm going to use the letter C, subscript C, to denote this conservative force. And the first case, this is not non-conservative, such as friction. Okay, so gravity is an example of this type of force whose total work done or on any self-enclosed complete loop is zero. Okay, it's not the only conservative force, but it's one of the few conservative forces we'll be encountering in the Physics 8 series. There are very few truly conservative forces, but they happen to be very important ones. Gravity is only our first example. You will see another example a little bit later. Okay, so you say, what's the big deal? Why is this important to have this contour integral to be zero? Well, let's see why this is important. Now, let's suppose you're no longer going from initial, going along a loop. Rather, you are actually going from initial to final state. Okay, so I'm not giving you two states, initial to final. Your job is to go from initial to final. Initial to final. Okay. Then you ask me, how do I get there? I say it doesn't matter. I don't care how you get there. So you say, all right, I'm going to take step number, path number one to get to the final. Okay, initial to final. Then I ask you, okay, go ahead and try another path. So I'm going to take a green path like this. I call it number 2. Okay. Then you ask me, how come you don't care about the which path to take? Well, my answer to you is that it doesn't matter. It's the same. If this force is a conservative force, okay, it makes no difference whether you take this red path or the green path. The work done by the force is the same. Do you believe me? Well, here's the deal. Let me ask you, suppose you take a round trip, okay, from, let's say, this point, round trip, and completely back. How much the total work done by friction, by this conservative, such as gravity? Well, that's zero, isn't it? I mean, that isn't that guaranteed by this equation, right? It's zero, right? So, for example, along the red path, let's say the work done by gravity or any other conservative force, let's say it's equal to 10 joules, okay, positive 10 joules. Gravity does positive 10 joules of work. Then isn't it true that on the way back, it has to do work of negative 10 joules, right? So from final back to initial, shouldn't do negative 10 joules of work because the total amount of work for this round trip is zero, right? Now, what if I don't go back from final to initial? Rather, I'm going from initial to final along this green path or path number 2. Then I'm reversing dr, right? Everything else is the same. Just reversing dr. How much work is done by gravity? Shouldn't that be positive 10 joules now? Right? So clearly that tells me whether you go along this red path or this green path, as long as you went from the same initial spot to the same final spot, gravity did the same amount of work of 10 joules. It doesn't have to be gravity. Any conservative force which satisfies this condition will get you the same thing, okay? And so that is the great advantage of a force being conservative, because you can start from the same spot, you finish at the same spot, you can take any path that takes you from initial to final. The work done by that force is always the same. This is guaranteed by the definition of a force being conservative, which is this condition right here again. Okay? Now, what is the advantage of that? You know, it sort of simplifies the calculation because it's path independent, right? Since it is path independent, okay, let me write down the path now. The path is, let me look at the work done now from initial to final, okay? Work done. Okay. W from initial to final. That's the definition of work done. But if it's a conservative force, okay, I'm going to highlight with red if it's a conservative force. It's worked up by conservative force. Then it is independent of the path, right? Path independent. It depends on initial and final. Depends on the force, but it does not depend on the path. And because of that, here is the important next step. I'm going to define this as u initial minus u final. Here, u is a new function. Don't ask me what the function is for now. Let me first ask you this. Is that possible? Is that legal to define this new function? Well, the answer is yes, because again, this integral from initial to final is independent of the path. Now you look at the right-hand side of this equation, ui minus uf. Nowhere did we mention the path. We only mentioned initial and final positions of this new function. There is no information about the path, right? And that is only possible if the force is conservative, because as the force is conservative, this integral has nothing to do with the path. If you look at friction, for example, you cannot possibly define a function u associated with friction because the integral will depend on the path. And therefore, the right-hand side without any information about the path is inadequate. Okay, but since the force is conservative, we are allowed to do that. And now we arrive at a brand new function u. And this u has a name. It's called potential energy. It is the second form of energy we have seen, besides the kinetic energy. And you probably already know this. It's common knowledge that energy comes in many different forms, right? I mean, later on you will see electrical energy, nuclear energy, you know, all kinds of energies. It's not just kinetic. Okay, so it's important to realize there are different types of energies. And this is only the second type called potential energy. Why do we define this potential energy? Because it greatly simplifies the calculation for the work done. Remember, we set out with this idea in mind, and that is we want to simplify the calculation of this work on the left-hand side of the work energy theorem, right? We don't want to deal with this integral, which is path dependent. So now it turns out this integral W is not path dependent if the force we're dealing with, the force that does work, is a conservative force, such as gravity, okay? So the left-hand side is no longer dependent on path. The left-hand side now becomes Ui minus Uf, with U being the so-called potential energy. What do we call potential energy? Well, look at this diagram. Go back to this diagram. You have some idea what we call potential energy. This guy at the top of the path doesn't have any kinetic energy, but he has the potential to turn his, potential energy into kinetic energy as he jumps down. The potential energy depends where he is, okay, depends on the location, okay? And he can convert that potential energy into the kinetic energy as he jumps downwards, okay? So that's why we use the word potential energy. All right. So in the next lecture, we're going to look at how we fit this potential energy, this new expression, into the work energy theorem and rewrite it in such a way that the work energy theorem becomes even cleaner to establish a direct bridge, a direct link between initial and final state, and find a quantity that does not change as you go from initial to final state. And that is exactly what we set out to do in the very beginning, right here. This quantity right here. What is this quantity? We'll see that in our next lecture.